You know, AI can actually be incredibly forgetful.
Oh, completely. It's notorious for it.
Yeah, like it often only remembers what happened just a few seconds ago. But just like that friend who forgets what you said yesterday but somehow remembers a $50 debt from 10 years ago, AI had to be taught how to have, selective memory.
Right, I had to learn what actually matters.
Exactly. So welcome to the Deep Dive. I'm your host.
And I'm your resident AI expert, ready to break it all down.
And looking at the massive stack of sources we've gathered for you today, ranging from foundational computer science papers to modern developer notes for PyTorch and Keras, our mission is really clear. We are unpacking exactly how an elegant piece of architecture called long short-term memory, or LSTM, totally solved AI's amnesia problem.
It's such a game changer. It turned these networks into absolute masters of knowing exactly what to remember and, honestly, perhaps more importantly, what to throw away.
Right, so to really appreciate what LSTM's accomplished, I feel like we have to look at the dark ages before they existed.
Oh, the dark ages of deep learning. Yeah, teaching a neural network to retain long-term context was arguably the single biggest roadblock in the entire field for a very long time.
Really, like the biggest.
Easily. I mean, engineers were just hitting a brick wall.
Well, I want to understand that brick wall. The sources talk a lot about the flawed system that came before LSTM, which was the Standard Recurrent Neural Network, or RNN.
Yeah, the standard RNN.
And my understanding is that, unlike a basic network where data just kind of washes over at once and spits out an answer, an RNN actually have loops. Like it passes information from one step to the next, like a chain.
Exactly. That structure is literally what makes them recurrent. They're trying to process sequences of data by keeping a kind of running tally.
Okay, a running tally.
Yeah, and for short-term context, this looping mechanism works beautifully.
I'm trying to picture this short-term context. Is it kind of like when my phone's autocomplete guesses my next word?
That is a perfect example, actually.
Like if I type the clouds are in the, it sees clouds and immediately suggests sky. The clue is right there next to the blank space.
Right. The gap between the relevant information and the place it's needed is incredibly small in that scenario. The standard RNN handles that with ease.
Makes sense.
The problem emerges when the real world stops being so neat and tidy. What happens when that context gap grows?
Give me an example.
Okay, imagine reading a book. The first chapter states, I grew up in France.
Okay, so the network reads France.
Exactly. But then that's followed by 20 pages describing a childhood on a farm. The weather, the food, tractors.
Right, lots of farm stuff.
And then a character says, I speak fluent.
Oh, I see the issue. The immediate recent information is all about farm animals, so the network is just totally distracted.
Exactly.
To know which language the character speaks, the network has to somehow reach all the way back 20 pages to retrieve the word France.
And in theory, the math behind standard RNNs suggests they should be able to connect that information. But in practice, they completely fail.
Wow. Why do they fail so badly?
Well, to understand the amnesia, we have to look under the hood at how a neural network actually learns from its mistakes. It involves a mechanism called backpropagation.
Right, backpropagation. I've seen that term all over the developer notes today.
It's fundamental.
So basically, the network makes a prediction, say, it guesses, I speak fluent cow, because it was just reading about farm animals.
Which would be hilarious, but wrong.
Right, it realizes it's wrong. Then it sends an error signal backward through the network to adjust its internal weights, basically saying, hey, pay more attention to the country mentioned earlier.
You've got it. The network calculates a gradient.
A gradient. No.
Yeah, which is essentially a mathematical slope that tells the model how much to adjust its internal dials to avoid making that exact same mistake next time.
Okay, so what's the problem with the slope?
In a standard RNN, as that error signal is passed backward through time, through all of those recurrent loops, the math turns against it.
How so?
At every single loop, the gradient is multiplied by a weight.
And if those weights are small fractions, I mean, I'm just doing the basic math in my head here.
Right, do the math.
If you take a fraction, say 1/2, and multiply it by another half, you get a quarter. Keep going, and it becomes an eighth, a 16th. It just shrinks.
It shrinks exponentially fast.
Oh, wow.
Yeah. By the time that learning signal travels backwards through 20 pages of text to reach the word France, the signal is basically zero.
So it literally can't learn it.
Exactly. This is what mathematicians famously call the vanishing gradient problem. The network simply stops learning those long-term dependencies because the signal telling it to learn has just vanished.
Let me try to workshop an analogy for this, because it feels like passing a handwritten note down a line of 50 people.
Okay, I like where this is going.
But the rule is, every person has to physically trace over the previous person's handwriting before handing it off to the next person.
Oh, that's good.
Right. By the time the note gets to the 50th person, the ink is just faded and blurred into this completely illegible smudge. The original message is totally gone.
The fading ink is a phenomenal way to visualize a vanishing gradient. And because of this fading memory, engineers realized they couldn't just keep tweaking the standard RNN.
They needed something totally new.
They needed a fundamental architectural shift. They had to find a way to let information travel long distances without degrading.
Like a VIP highway for data, completely insulated from the fading ink problem. Which brings us to the hero of our sources today, the LSTM.
Yes, enter the LSTM. And the core innovation here is something called the cell state.
The cell state.
Yeah, if you look at the equations in the research papers, it's usually represented as C sub T.
Okay, let's look at the cell state. Because the diagrams in the papers draw it as this straight line running right across the very top of the network module.
It does look like that, yeah.
Is it just a dumb pipe? Like, does it just blindly carry data from point A to point B without anything touching it?
It operates much like a conveyor belt running straight down the entire chain of the network. But what makes it special is that it only has very minor linear interactions.
Okay, what does that mean in plain English?
Well, standard networks force data through really complex squashing mathematical functions at every single step. That's what distorts the data over time.
That's the fading ink.
Exactly. The cell state bypasses most of that, making it incredibly easy for information to flow along it completely unchanged.
Wait, if it's highly protected but still influences everything the network does, it's not really a dumb pipe. It's more like a company's core strategic vision.
Oh, interesting. How so?
Well, you have employees quitting, new projects launching, departments totally reorganizing, but that core vision remains intact, right? It sits above the noise, guiding the company over the years.
The cell state definitely functions like that core vision, but, a company's vision does occasionally need to adapt to new market realities, right?
Sure.
The LSTM does have the ability to carefully add to or remove information from that conveyor belt. It just doesn't happen randomly.
How does it control it?
The network uses very specific structures called gates to control the flow of information.
Gates. Okay, so to manage this VIP highway, the LSTM acts like a ruthless, highly organized executive assistant filtering the CEO's emails.
That's exactly what it is.
The sources detail 3 specific gates. Let's break these down because the mechanism here is fascinating.
Let's do it. The very first gate the data encounters is called the forget gate.
The forget gate.
Right. This is where the network decides what information it is going to throw away from the cell state.
I stumbled on that when reading the papers. The very first step in a quote-unquote memory network is deciding what to forget.
It sounds counterintuitive, I know.
Yeah, why wouldn't it prioritize remembering first?
Because space and relevance are at a huge premium. If you don't clear out the obsolete data, the new data lacks context or it just gets confused.
Oh, that makes sense.
So the forget gate looks at 2 things. The previous hidden state, which is the network's short-term memory of the last step, and the current new input.
Okay.
It passes both of those through a sigmoid layer.
Let's pause there, because terms like sigmoid layer can alienate people who aren't knee-deep in calculus.
Fair point.
Why a sigmoid? What is it actually doing to the data?
Think of a sigmoid function as basically a squasher. It takes any number you feed it and squashes it into a value strictly between 0 and 1.
Between 0 and 1.
Yeah, and it calculates this for every single piece of information in the cell state.
So it's basically a percentage. Like 0 means 0%, destroy this completely, and 1 means 100%, keep this entirely.
Precisely. Let's apply it to a language model to see it in action. Imagine you're reading a paragraph about a character named Jane.
Okay, tracking with you.
The cell state has remembered Jane's gender, so it can correctly predict pronouns, like she or her in upcoming sentences.
Right.
But suddenly, the narrative shifts, and the next sentence introduces a dog named Spot.
Oh, I see the danger. If the cell state rigidly holds on to Jane's gender, the network might start calling the dog she when predicting the next word.
Exactly. So the network sees the new subject, Spot. The forget gate evaluates this shift, and it outputs a 0 for the specific numbers in the cell state that represent Jane's gender.
It just wipes it out.
It actively deletes that context to avoid confusing the pronouns moving forward.
The ruthless executive assistant just threw out the old file. I love it. Okay, so once the obsolete junk is cleared out, the network needs to process the new reality.
Right, and that happens at the second gate. The input gate, which is sometimes called the learn gate.
The learn gate.
Yeah, this gate's entire job is to decide what new valuable information should be stored in the cell state to replace what was just thrown away.
Does it just shove the new word into the cell state, or is there a filtering process here too?
Oh, there is definitely a filtering process. It's a highly calibrated two-part process.
Guide me through it.
First, it uses another sigmoid layer. Just like the forget gate, this sigmoid decides which specific values in the cell state we are going to update, outputting numbers between 0 and 1.
Okay, so finding what to update.
Exactly, but alongside that, there is a ton layer.
Okay, another math function. You mentioned the sigmoid squashes things between 0 and 1. I saw in the notes that ton squashes values between -1 and +1.
You did your homework.
Well, I try, but why do we need a different range here? Like, why negative numbers?
The range is the secret sauce. A sigmoid is a gatekeeper. It can only say, let this through or block this. But a ton layer is creating the actual new candidate values.
So it's creating the new data.
Yes. And by allowing negative numbers, the network gains the ability to actively subtract from or decrease the importance of a state, while positive numbers allow it to add or strengthen a state.
So it's not just a bouncer at the door. It's someone sitting at a mixing board adjusting the dials up and down. The -1 turns the bass down, the +1 turns the treble up.
A mixing board is a great way to think about it. The network takes the output of the gatekeeper, the sigmoid, and multiplies it by the new candidate values from the ton layer.
So they work together.
Right. It scales the new information by exactly how much it decided it was worth updating, and then adds that final result to the cell state.
Going back to our story, this is where the network actively locks in the fact that the new subject is a dog, turning off the dial on the pronoun expectation for it, while leaving the dials for things like the weather or the location completely untouched.
Exactly. The cell state is now officially updated. It has successfully forgotten the obsolete subject and learned the relevant new one.
Okay, so we have one gate left. The assistant deleted the old email, drafted the new strategy document, and put it in the core vision folder.
Yep.
But if the cell state is this protected internal VIP highway, how does the rest of the network actually see what's going on so it can make its final prediction?
It uses the third and final gate, the output gate or the use gate.
The output gate.
The network needs to reveal information, but it doesn't need to shout everything it knows all at once. The output is going to be based on our newly updated cell state, but it will be a heavily filtered version.
How did the filtering work here?
More squashing? You guessed it. First, the network runs a sigmoid layer over the current input to decide what specific parts of the cell state it wants to output right now. Okay. Then it pushes the entire cell state through a ton layer to normalize all the values between -1 and +1. Finally, it multiplies those two things together.
So the network looks at the current word, uses the sigmoid to say, I only need 50% of the grammar rules right now, and pulls exactly that from the normalized cell state.
Precisely. Let's say the network just processed our new subject, the dog spot. It might use the output gate to specifically reveal whether that subject is singular or plural.
Why just that?
Because if the very next word it has to predict is a verb, the network needs to know how to conjugate it correctly. It doesn't need to output the fact that Spot is a dog, just that there is only one of him.
You know, here is where it gets incredibly profound for me. When you look at those three gates working in tandem, forget input, output. The brilliance of LSTM isn't just about having a bigger hard drive to remember everything.
Got it all.
We call it a memory network, but the architecture is essentially a philosophical exercise in choosing exactly what to let go of.
That is a beautiful way to put it. And because it mastered the art of selective forgetting, LSTM completely revolutionized the tech world.
Really, like everywhere.
Oh, yeah. It solved that vanishing gradient problem, which meant engineers could suddenly train networks on vastly longer sequences of data without the learning signal dying out.
Now, the sources list an overwhelming number of applications, but I want to anchor this in reality for a second. Where did you and I actually see LSTMs changing our daily lives or the economy?
Well, they became the absolute gold standard for time series prediction. Take a classic, really complex problem, predicting the number of international airline passengers over several decades.
That seems like a total nightmare to predict. You have summer travel spikes, winter lulls, economic recessions, fuel price shocks. It's not just a straight line going up.
Exactly. A standard RNN would get distracted by a sudden dip in travel during a single bad month and completely ruin its long-term forecast.
Ah, I see.
But an LSTM using its cell state could remember the multi-year growth trend while using its forget gate to filter out the short-term noise of a single bad winter storm.
That explains why the financial sources mention them so heavily. I was reading these case studies about hedge funds deploying LSTMs to analyze historical stock price data for companies like Apple, Amazon, and Microsoft.
The stock market is the ultimate noisy sequence. An LSTM could learn that Apple's stock usually surges around a new iPhone release.
Right.
And the forget gate would ignore the daily volatility like the random Tuesday dips, while the sell state held on to the broader quarterly momentum. It outperformed traditional financial models by a wide margin.
That's incredible.
And beyond finance, it became the invisible backbone of the 2010s. Machine translation, handwriting recognition, speech to text. If you used voice dictation on your smartphone 5 years ago, you were relying on an LSTM network.
Okay, I'm waiting for the other shoe to drop here.
Yeah.
If they are this powerful, why aren't they the only thing we use today?
Because they have fundamental structural flaws. They are incredibly elegant, but they are not magic.
Lay out the reality check. What actually breaks an LSTM?
First, they are computationally heavy. Because of those 3 gates we just broke down, an LSTM has a massive number of mathematical parameters compared to a simple RNN.
That makes sense.
All those sigmoid and tan functions running at every single step make them very expensive and extremely slow to train.
But computing power gets cheaper every year. Couldn't we just, throw a massive cluster of GPUs at the problem and brute force the training?
You would think so, but that leads to their fatal flaw. They are almost impossible to run efficiently in parallel.
Really? Why?
Think about the architecture we just discussed. An LSTM processes sequences strictly one step at a time. The cell state at step 10 depends entirely on the calculations finished at step 9.
Ah, see the trap. You can't process word number 10 on a separate GPU because word 10 is sitting there waiting for word 9 to hand over the updated cell state.
Yeah.
It's a sequential bottleneck. No matter how many lanes you add to the highway, the cars still have to go single file through the toll booth.
The toll booth is a great analogy. The sequential bottleneck is unavoidable. And furthermore, even with the VIP highway of the cell state, memory isn't infinite.
Right. It has limits.
If a sequence is incredibly long, say you are trying to feed the network an entire 500-page novel at once, the cell state eventually gets overcrowded. The LSTM will start dropping crucial context.
Which is exactly what forced researchers back to the drawing board. They hit the ceiling of sequential processing and had to ask a really profound question.
Which was?
Do we really need this complex memory pipeline at all? Or do we just need a way to look at the whole sequence at once and know what specific parts to pay attention to?
That exact line of questioning paved the way for the invention of transformers. They threw out the recurrent loops and the sequential bottleneck entirely in favor of attention mechanisms.
Which could be massively parallelized across GPUs.
Exactly. But transformers are definitely a deep dive for another day.
Oh, for sure. I want to bring this back to the learner listening right now. Looking at the developer notes we gathered, especially for someone transitioning their career into data science or someone opening up PyTorch for the first time,
Right.
what is the big takeaway they should pull from the era of LSTMs?
The fundamental lesson from studying LSTMs is understanding that sequences are a unique beast. Whether you are dealing with a string of English text, the fluctuating waveform of an audio file, or the daily closing prices of Amazon stock.
You're dealing with data where the specific order is the most important feature.
Yes. If you take a sentence and scramble the words, it loses its meaning entirely. Scramble the stock prices, and the multi-year trend disappears. The order is the data.
So for anyone staring at code syntax in Keras or PyTorch, feeling intimidated by setting up batch sizes, hidden dimensions, or time steps, what's your advice?
My advice is to take a step back from the syntax, focus entirely on the information flow.
Because the calculus and the code are just tools to solve a flow problem.
Exactly. Ask yourself, how does my data physically move through this architecture? Once you conceptually grasp how a piece of information from step 1 needs to survive until step 50.
Once you understand the need for the VIP highway, the strategic forgetting, the mixing board updates,
Writing the code is just basic execution. You're just giving Keras instructions to build the gates you already designed in your head.
framing the math as just a mechanism for moving information takes so much of the intimidation out of it.
The conceptual understanding of why the architecture exists is the real skill. The coding is completely secondary.
That is so true. Well, that brings us to the end of our stack of sources today, but I want to leave you with a final thought to mull over.
Oh, lay it on us.
We often say that human wisdom comes from life experience, and AI's wisdom comes from massive amounts of training data. But the specific genius of the LSTM model, the very reason it broke through the amnesia barrier, proves something deeply profound about both humans and machines.
What's that?
True wisdom doesn't come from hoarding every single piece of information. It actually comes from knowing exactly what is safe to forget.
Finding the signal by intentionally dropping the noise.
Exactly. Next time, we're going to shift gears. We spent today exploring how AI remembers. Next, we're going to explore how AI sees.
Oh, that's going to be a fun one.
We'll be diving into convolutional neural networks, or CNNs. How does a machine look at an image when it doesn't have eyes? It slides mathematical filters over raw pixels to extract features like edges and textures.
It is mind-bending stuff.
It really is, and you definitely won't want to miss it. Thank you so much for joining us on this deep dive into the source material today. If you enjoyed unpacking this with us, please hit that subscribe button. We'll see you next time.